Okay. So at the end of last class, we were working on this problem where hydrogen emits a line of infrared radiation with a wavelength of 1282 nanometers. The first question was, what energy level did the electron relax to? Well, anytime you're getting infrared radiation, that means that the electron relaxed to 3. The thing to keep in mind is ultraviolet radiation. It means N sub F is equal to 1. If it is visible light, N sub F is equal to 2. And if it is infrared, N sub F is equal to 3. Yes, you can have other forms of light, but you don't need to worry about those particular forms of light. I will stick to the 3 series that are listed here. So we know that it relaxed to an N sub F of 3. We have been asked, where did the electron relax from? Anytime we're talking about the energy level, if you see energy level, that means you're going to be using the Rydberg-Balmer equation. So 1 over the wavelength is equal to R times 1 over N sub F squared minus 1 over N sub I squared. So our value was 1 over 1282 nanometers is equal to 1.097 times 10 to the minus 2 per nanometer times 1 over 3 squared minus 1 over N sub I squared. A lot of times the first thing I do is I simplify fractions. You do have to be somewhat careful to leave enough values, but it's just easier if you simplify the fractions to work with. So 1 divided by 1282 is 7.800 times 10 to the minus 4, and that is per nanometer. That's equal to the 1.097 times 10 to the minus 2 per nanometer times 1 divided by 3 squared is 0.111 minus 1 over N sub I squared. The next thing I do is I go ahead and I divide by the 1.097 times 10 to the minus 2 on both sides. So 7.800 times 10 to the minus 4 divided by 1.097 times 10 to the minus 2. That gives us a value of 0.0711. That is equal to 0.111 minus 1 over N sub I squared. The next thing I do is I subtract the 0.111 from both sides. And when you do so, you get a negative 0.03989 is equal to a negative 1 over N sub I squared. My next step is to multiply by a negative 1 so that both sides become positive. At this point, I use the inverse key on the calculator, which is x to the minus 1. And that gives me a value of 25 is equal to 1 over n sub I squared. I'm sorry. It's equal to n sub I squared. And then you take the square root of both sides, and you get an n sub I equal to 5. What this means, with respect to the energy associated with this electron, is we have our nucleus. Surrounding the nucleus are these energy levels. What it means is that an incident beam was shined on this electron in hydrogen, and it caused the electron to bounce to energy level 5. Then when the electron relaxed from energy level 5 down to 3, a wavelength of light equivalent to 1,282 nanometers was obtained. Again, you're not just exciting one electron at a time. We're exciting all of the we're exciting atoms that contain electrons. And so these transitions, they're occurring simultaneously that we observe. It's just we can only see the ones in the visible spectrum. We cannot see the ones in the ultraviolet or infrared spectrum. But we can detect them using other types of instrumentation. And they are there. Now, when I ask you to solve for the energy associated with a particular transition, the equation that you're going to use is that the energy of the electron is equal to the energy of the final state minus the energy of the initial state. We can use our energy equation, and what comes up is energy of 2.18 times 10 to the minus 18 joules times 1 over n sub f squared minus 1 over n sub I squared will give you the energy. So we're going to use this equation to solve for the energy. So our energy is going to equal the 2.18 times 10 to the minus 18 joules times 1 over 3 squared minus 1 over 5 squared. When you key this into the calculator, you will get an energy of, and there should be a negative here, an energy of a negative 1.55 times 10 to the minus 19 joules. I want to discuss why it's negative. A lot of times when you've worked in math, you think of negative and positive in a different light than the way a chemist tends to think of negatives and positives. What this means when we have a negative is it's telling us whether energy is generated as a result of the process or whether it is absorbed as a result of the process. If energy is negative, it means that energy is generated. If energy is positive, it means that energy was absorbed. The reason this one comes out to be negative goes back to the diagram that I just showed you. What are we looking at? We are looking at this transition where 1282 nanometers of light is generated. We're looking at the energy being generated and given off by the electron relaxing. If I would have been talking about if I would have been talking about the absorption of the electron, now this energy would have been positive because the electron itself, which is our system, is absorbing the energy. But because I was specifically talking about this one, energy is negative. Questions? Okay. Then let's move on to quantum numbers. With the start of this information, you need to be a little bit patient. The reason you need to be a little bit patient is because we're going to talk the theory, and we're probably only going to get through the theory today. Then on Tuesday, we're going to start applying the theory when we start dealing with electron configurations. So you got to be a little bit patient because there's a lot of theory that's going to go into the electron configurations. Okay. If you'll recall, we started the discussion about light by saying an electron can behave as a wave or it can behave as a particle. This is the wave-particle duality nature of an electron. Now, waves they are in motion. So they have a velocity. Particles have a mass. The problem with the wave-particle duality of nature is if you can stop the electron to get its mass, you can't see its velocity. You can't see its speed. But if you watch the speed of the electron, you can't get the mass. So you can't know both pieces of information simultaneously. These are complementary properties, and there is an uncertainty to it. It can be described as a particle, and we can get the matter, and we can get the mass, and we can know its position. Or it can be described as a wave, and we can get the wavelength and the frequency. But you can't observe both concepts simultaneously. That's because they are complementary partners. But they can't be measured at the same time. This led to what is known as the Heisenberg uncertainty principle. Which literally states you can't know the mass and the velocity of an electron at the same time. Now, if you'll recall, I said that in lab, I made a point of saying that the electronic structure, the behavior of the electron determines how an atom behaves. Well, if we can't know both pieces at the same time, how can we figure out the electronic structure? That is where Schrodinger comes into play. The Schrodinger equation is the psi of H is equal to the psi of E. And what the Schrodinger equation does is it allows us to calculate the probability of finding an electron of a particular amount of energy at a particular location in the atom. Solutions to the Schrodinger equation produce many wave functions. And basically, folks, the Schrodinger equation, it's not so bad to solve the Schrodinger equation for a hydrogen atom. But once you start getting into electron-electron repulsions, multiple proton-electron attractions, it gets complicated fast. We have supercomputers that are necessary in order to calculate the Schrodinger equation in a reasonable amount of time. Now, with this Schrodinger equation, we can solve the Schrodinger equation, and if we plot the distance versus psi squared, what we obtain is an orbital. And all this orbital is a probability distribution map. For example, one possible orbital is that of an s orbital. What we're describing is that the electron is likely to be somewhere in this sphere. That's what we mean by an electron density map, a probability distribution map. Or we can have a p orbital. And when we get a p orbital, what we're doing is we're describing that the electron is most likely somewhere in one of these two lobes. So again, a plot of sides squared versus the distance represents this probability distribution map. We're not going to solve the Schrodinger equation. We're going to use its results. We're going to use the results to understand the most probable location to find every single electron in an atom of an element. The results of that calculation give 3 quantum numbers. The results of this calculation give 3 quantum numbers. I'm trying to let people catch up to me. Let's see if I can blow this up a little. Okay. The first quantum number that the Schrodinger equation generates is known as the principal quantum number. The principal quantum number is represented with a lowercase n value. We sometimes refer to this principal quantum number as the energy level or the shell. And what this principal quantum number is specifically doing is it's describing how far from the nucleus the electron resides. To help you picture this concept of an energy level or a shell, let's think of an onion. You have the center of the onion. The center of the onion would represent the nucleus. Then we have layers surrounding that center of the onion, and those layers steadily become larger and larger. Those are our shells. The shell closest to the nucleus, the shell closest to the center, will have the value of n is equal to 1. The first shell. The second layer away from the nucleus will have the n is equal to 2 value. Shell number 2. The third layer away from the nucleus will have n equals 3. The third shell, the third layer. So you have your principal quantum number. Again, it tells you how far from the nucleus the electron resides. Is it right next to the nucleus in shell 1? Or is it further out in shell 7? The next quantum number that the Schrodinger equation generates is called the angular momentum quantum number. It is represented with a lowercase l. Typically, we make that lowercase l italicized, or cursive, just so that we can differentiate it from the number 1. But it is an L. The angular momentum quantum number tells us the orbital type or the subshell. Is it that S that I showed you a moment ago, which is a sphere? Or is it a P, which looks like dumbbells? Or is it a D, which looks like a clover leaf? When we calculate L, that is what we're obtaining, is we're obtaining the shape of the orbital. The third quantum number is known as the magnetic quantum number. It is represented with an M, a lowercase m sub L. This tells you where on the XYZ coordinate plane you're most likely to find the electron. It tells you the specific orbital in the subshell where you're most likely to find that electron. Now, the last quantum number is not a result of the Schrödinger equation. It's actually the result of what we will call the Pauli exclusion principle. Basically, the Pauli exclusion principle says no two electrons can have the exact same four quantum numbers. We find ourselves in need of a fourth quantum number in order to maintain the Pauli exclusion principle. The fourth quantum number is referred to as the spin quantum number and is represented as a lowercase m sub s. The spin quantum number is literally describing the orientation of the spin associated with the electron. Is it moving left or is it moving right? Now, standard notation is to include a +1/2 first, a +1/2 spin first. Then, if an orbital has a second electron, that electron will have a -1/2 spin. So it's standard notation to do the +1/2 first. Folks, what I just described to you is not much different than an address. You can think of the shell as being like, when, let's say we're trying to find where you are right now. The shell would be the state of Arkansas. That's our biggest piece of information. Then we get into the angular momentum quantum number, the subshell, which describes that you're in the city of Conway. So we've narrowed it down. Then we get to the magnetic quantum number that says you're in Maine in 104. What, where am I? We've narrowed it down further. The spin would be like putting you in the seat you're sitting in. So it's like an address, but it's an address for an electron. Okay. So with the principal quantum number, we're focusing strictly on this column at the moment. The principal quantum number can be any whole number. 1, 2, 3, 4, 5, 6, 72. It can be any whole number. And again, what that principal quantum number is doing is it's describing how far from the nucleus does the electron reside. Is it right against the nucleus? If so, that's why n is equal to 1. Is it in the second shell away from the nucleus? Is it in the third shell away from the nucleus or the fourth shell away from the nucleus? How far away from the nucleus does that electron reside? You will notice this is related to the energy. Just hold it until the end of class. Yes.
So if you're like moving electrons, how do you know that almost like that? So would this help you find like the excitement and then the relaxation of it?
This is the same thing we were dealing with the light. When we took the electron from hydrogen, which had to be, when it is in its standard state, the electron is as close to the nucleus as possible in that first level. And then we excited it to an outer level. So this is the exact same thing we were doing with light. But an electron that is excited is unstable, and so therefore it wants to relax. And depending upon where it relaxes to will determine the type of radiation that's given off. So when we were talking about the Rydberg-Balmer equation and how light behaves for hydrogen to obtain the atomic emission, we were focused on the principal quantum number. Now, the angular momentum quantum number, L. L can be any value from 0 to an n minus 1. So if n is equal to 1, that first shell away from the nucleus, then L can be anything from a 0 to 1 minus 1, which equals 0. So in other words, L is equal to 0. If n is equal to 2, L can be equal to 0 to 2 minus 1, which is 1. So in other words, L can be equal to a 0 and a 1. These I know just represent numbers to you right now. But this is the formula you use to figure out L. Now, what does it mean? Can you put this in something besides 0, 1, 2? I don't understand numbers with respect to electrons. What does it mean? Well, when L comes out to be 0, we're talking about an S subshell, which just happens to be a sphere. When L is equal to 1, we're talking about a P subshell, which means that it is going to be one of these 3 dumbbell-shaped orbitals. If L is equal to 2, that means we have a D subshell, and it will be one of these 5 shapes for the orbital. And if L is equal to 3, that is going to be the F subshell, and it will be one of these 7 orbitals. So let's take a moment. Up here, I said when n is equal to 1, when the principal quantum number is 1, when you're in that first shell away from the nucleus, the only subshell you can have is an S subshell. That's it. Now, when n is equal to 2, meaning you're now in that second layer away from the nucleus, you have the opportunity to have L is equal to 0 and L is equal to 1, which means you're going to have the S subshell and you're going to have the P subshell available to you. The electron will be in one. If it's in the S subshell, it will be in the sphere. If it's in a P subshell, the electron density map is telling us that it will be in one of these lobes. So you have your angular momentum quantum number. So now we're getting into the second column here. We talked about n is equal to 1, L equals 0. That was its only option. That's why you have just a 1s in the first shell. When n was equal to 2, we had the option of L of 0 or 1. That's why you had the 2s and the 2p subshells. If n is equal to 3, L can be anything from a 0 to 3 minus 1, which is equal to 2. In other words, L can be a 0, a 1, or a 2. Because of that, you have the 3s, 3p, and 3d available. We could continue this process and do n is equal to 4, and you would find that the L options for n equals 4 is 0, 1, 2, and 3. That's why in the fourth shell, you have the 4s, the 4p, the 4d, and the 4f. At this time, F is as high as we go with respect to elements. But if we go past that, then we do it alphabetically. So the letter that comes after F would be D. So the next thing would be a G. Yes.
Subshells kind of overlap, like the electron can be in any of these, like there's more places it can be found if you're in a higher shell.
If we're talking about hydrogen with its one electron, and we have excited that electron, yes, we could have excited it into the 4s or the 4p. It just would be in one of these 4 subshells. Now, what we're going to see when we actually get into multi-electron systems is we actually, the reason this is so useful is because we actually will start to fill it in this particular order. But if we're talking a one electron system, and yes, basically if we excite an electron, whether it's in a one electron system or a multi-electron system, if you excite an electron, it just has to be in one of the subshells in a higher shelf. Yes. I thought I saw it here. No. Okay. Stretch. Gotcha. Questions so far? Magnetic quantum number. The M sub L, the formula is that it can be anything from a negative L to a plus L on a number line. So when L was equal to 0, M sub L, would it be anything from a negative 0 to a plus 0 on a number line, which means it's equal to 0. What this is telling me is that there is only one orbital in the S subshell. When L was equal to 1, then it could be a negative 1 to a plus 1. If you look at that, that means it on a number line, it could be a negative 1, a 0, or a 1. Any of these 3 numbers. 3 numbers. 3 orbitals. When L was equal to 3, if let's say L is equal to 3, whoops, nope, don't go back. That means that we're talking about a negative 3 to a plus 3 on a number line. So it could be any of these 7 numbers. That is why L of 3 has 7 orbitals. questions? So in other words, the IMSABEL, folks, really is telling you, while it's a magnetic quantum number and it tells you where on the XYZ coordinate plane the orbital resides, it's also telling you how many orbitals can be in a particular subshell. So when N is 1, all we have is an S subshell. And there is only one orbital in the S subshell. When N is equal to 2, the second layer from the nucleus, L was equal to 0 and 1, meaning that we had a spherical S subshell and we had 3 p orbitals, according to the IMSABEL. When N is equal to 3, our options for L were 0, 1, and 2. Meaning we had S, P, and D. Now, if you calculate IMSABEL for the S, you would find only 1 orbital. It has only 1 IMSABEL value. For the P, you would find that it has 3 orbitals because it has 3 IMSABEL values. For the D, which is L is equal to 2, you would find that it has 5 orbitals if you do the IMSABEL value. When you get to level 4, N equals 4. That means we're talking the 4th layer away from the nucleus. We have the possibility of L being 0, meaning an S. We have the possibility of L being equal to 1, meaning P's. We have the possibility of L equal to 2, meaning D's. And we have the possibility of L equal to 3, meaning F's. The dot, dot, dot means that basically, yes, we're carrying the same story. So N equal 5, you have the possibility of S, P, D, and F. You also have the possibility, technically, though it doesn't exist yet, of a G. When N is equal to 6, you have the possibility of S, P, D, F, G, and H. Notice, folks, that the number of subshells that you can have is equal to the principal quantum number. So when I had principal quantum number 1, I only had 1 type of subshell. When I had principal quantum number 2, I had 2 types of subshell. When I had principal quantum number 3, I had 3 types of subshell. The other thing I would make note of is IMSABEL. We graduate those IMSABELs, meaning the number of orbitals in each subshell, by odd numbers, 1, 3, 5, and 7. Now, this is just another way to take that previous slide and the energy slide and combine them. So literally 1s, we only had one orbital, so we only have one line. When you have the second shell, you had S subshell and P subshell. The S subshell only has one orbital, so one line. The P subshell had 3 orbitals, so 3 lines. When you had the third shell, you had S, P, and D subshells. The S had only one orbital, so one line. The P had 3 orbitals, so 3 lines, and the D had 5 orbitals, so 5 lines. So this is just another way to take that information that was on the previous slide and not do all the drawings, but be able to condense it. Now, I said that this also is related to the energy. This is increasing energy. When we start working with a multi-electron system, with any electron system, we always go from the lowest energy, which is going to be the one closest to the nucleus. We always go from the lowest energy up. Now, you'll notice that there is a pretty good distance between the first shell and the second shell. The distance between the second shell and the third shell is also reasonably decent. But as you get further out, the distance between those shells, the N is equal to 1, 2, 3, 4, 5, 6, 7. The difference between those energies becomes less and less. Now that's important because when we start talking about a multi-electron system, what we're going to see is that due to all of this, the 4s and 3d are actually very close in energy. And what we do is we wind up with a crossover. The same thing will go with the 5s, 4d. They're actually pretty close in energy. And so we wind up crossing over some electrons. That's going to be important when we start dealing with the transition metals. And it's also going to be important when we deal with some anomalies. Now, when we write the 4 quantum numbers for an electron, remember, all 4 of these quantum numbers is describing just one electron. When we write them, we always write them in this order, where we write the shell, how far away from the nucleus it is, the subshell, what does the orbital look like, the magnetic quantum number, where on the XYZ coordinate plane is it, and then the spin quantum number. We always write it in this particular order. Now, one of the things that you will see on your test is you will have to determine whether a set of quantum numbers is valid or whether it is invalid. How do you know? Basically, if it follows the rules that I've laid out, it is valid. If it doesn't follow the rules that have been laid out, it is invalid. What are those rules? Well, N has to be equal to a whole number. L has to be anything from 0 to n minus 1. So it's based off of that n value. M sub L has to be anything from a negative L to a plus L. So in other words, it's based off of the L value. Notice each one is based off of the value preceding it. And then M sub S only has two options. It has to be a plus 1/2 or minus 1/2. So it's valid if it follows the formulas that you have been given. It's invalid if it doesn't. Questions? Again, it's valid if it follows the formulas. It's invalid if it doesn't. And what I mean by that is it has to follow step by step by step by step. If any one of these steps is broken, then it's an invalid set. So let's look at some examples. The first one reads 3, 4, 0, 1/2. Okay, well, n can be 3. But if, what are you doing? We know that n can be 3, but that means, let's try a different pen. But if n is equal to 3, that means L has to be 0, 2, 3 minus 1. So it has to be a 0, a 1, or a 2. Those are its only options. So this one is invalid because of the L value. L cannot be a 4. The next one, well, n is fine. N can equal 2. That's not a problem. L is going to be equal to 0, 2, 2 minus 1, meaning that it can be a 0 or 1. So that's okay. M sub L has to be equal to a negative L to a plus L. So that can be a negative 1, a 0, or a 1. So that is okay. And then M sub S has to be either a plus 1/2 or a minus 1/2. So that is okay. So this second one is valid because it followed the rules. Yes. Okay. Yes. But when we're talking about is it a valid set or invalid set, all it has to do is follow the rules. So It can be either a +1/2 or a -1/2. When we start filling the electrons in to the actual atoms, then we'll put the +1/2 in first. But for this particular part, all we're doing is looking, is it following the rules? So I want you to do the next one, which is 2, 1, 3, 1/2. And tell me whether it's valid or invalid. And which, if it's invalid, why is it invalid? Again, you will have 2 or 3, maybe even 4 of these on the next exam. So if you're one of those that likes to put a star by the type of problem you'll be doing, I recommend it. This is also one of your optional homeworks. We're only going to do a few of them. But it's an entire series where you can work on valid or invalid. Okay. How many people say it is valid? How many people say it is invalid? Okay, the majority say it's invalid. That's good. Now, which letter is invalid? Is it N, L, M sub L? Was M sub S invalid? No, always check all of them. So yes, folks, this was invalid because of the M sub L value. Basically, if L is equal to 1, then M sub L has to be a -1 to a +1. Therefore, it couldn't be 3. Tell me about the next one. -2, 1, 0, -1/2. -2, 1, 0, -1/2. Decide if it's valid or invalid. How many people say it's valid? How many people say it's invalid?
Yeah.
Majority say it's invalid. That is correct. Was it, now, is in valid or invalid? It's invalid. It has to be a positive whole number. So that, right off the bat, N is below. The rest of it was a possibility. But because of N, it was invalid. Let's try one more. 322 negative 1/2. Three, two, negative 1/2. Is it valid or is it invalid? How many say it's valid? How many say invalid? It is valid. It followed the rule. I know they look like numbers, but they actually mean shape and location. Okay, so on Tuesday, we are going to talk about that L value a little bit more because we're going to talk about the shapes, because each of these shapes, when you start with the P subshell by itself, or once you get into the 3 Ps, we start getting what's called nodes. These are going to be locations where the electron cannot exist. And we're going to talk about those nodes in greater detail on Tuesday, and then we're going to get into the periodic tables arrangement and then into electron configuration. Because all of these numbers, except for the M sub L value, every single one of these numbers can be found on the periodic table. So we're going to see how we translate this into that when we get into electron configurations. Okay, I will see you Monday for lab. If you have lab to turn in, or if you are absent on Monday, if you are absent, I have your lab, your exam. You can come pick it up.
Okay, apparently I still don't understand this. So I was gonna ask, because when I put it in my calculator, I did not get -0.7 to the left, or no 0.7. Like I keep getting
1 divided by 1282
and then we got this.
divided
Yeah,
by 1.09750 negative 2.
How does yours give the decimal though? Mine does not.
Okay, are you using the E button or are you using parentheses and?
parentheses and stuff, so I need to use the E.
You've got to, well, no, you can use the parentheses, but if you forget a single parentheses, you will have just messed up everything.
So I need to use the office store.
That, I find the E much easier.
Okay, perfect, thank you.
Excellent. Good deal.
And I have lab. Come good name.
That's.
Josh Haley. That's the period.
One pair, yeah, that's fine. Oops, I was using it.
Anastasia.
Huh? Which lab are you in?
I'm in
8, 11, or 2?
8
I think that's this one. I don't know. Oh, but it doesn't. Okie dokie.
Thank you.
Never been able to wrap my head around how observing something like changes with behavior. Do you have any way to explain that to me?
Let me ask you a question. If a car's flying, if you're standing still, and a car's flying down the road, can you tell me everything about that car? That's because you could tell me more about its velocity, but you couldn't tell me its speed. Because you can't do the two things at the same time. Is that helpful?
Yeah, so kind of like when we talk about like just observing something, not really specifically measuring it.
Right, it's, another example is Schrodinger's cat, the Schrodinger's cat.
Yeah.
idea. You can't tell me whether the cat is dead or alive unless you observe it when you put it in the box. So you can't, and the only way to observe it is to open the box. So you can't do two things at the same time.
Yeah.
The car idea is probably the
Yeah.
most accurate for what.
Yeah,
we're
like
trying
the
to
cat one always throws me off because like, I don't know, the normal logic is like, okay, it's still one of those though.
do. It is
So
one of
observe,
those.
but like,
Yeah.
with like electrons, they're kind of both particle and wave
Right.
until you measure it as one.
You measure one of them, like my car, I
Yeah.
can measure the mass of the car, but I can't do it if it's moving. The only way to tell the velocity is if it's moving, but then I can't measure its mass because it's not standing still. So the car idea would be the most useful for you.
Yeah. That makes sense. Yeah.
So think of an electron as a positive.
Yes.
Okay.
I love quantum physics, but it is so hard to wrap my head around any of it.
It is, it's a
I
challenge.
always thought if I had like a little more understanding of it, like that's something I'd love to study, but I don't know what I'm saying.
I